So in this video I want to discuss the Dedekind cuts representation of the real numbers. So firstly let's just discuss what the real numbers are. So the real numbers, the way I like to view it, is that the real numbers is the set of symbols such that every symbol in that set represents a point on the line. So you take the continuum, which is the line, and you have a set such that every point on the continuum line has an element in that set, and we can label these elements with whatever silly symbols we want. So we could label this point with the element 0 here, so that will correspond to that element there. We could label this point with symbol 1, and that will correspond to that point there. But the point is that every point on the continuum, on this one-dimensional continuum, will have an element in the set of real numbers that corresponds to it. So pi will have the point at length pi from here will have a point in that set, and etc. Okay, so what we now want to ask is, how do we actually characterize this? How do we actually construct this set? And that's quite a difficult question. You may think you already know how to construct that because you've been doing it for years. You have the integers 0, 1, 2, 3. Then you have some fractions, half, 3/2, and then you have some irrational numbers like the square root of 2, and then you have some transcendental numbers like pi. The problem is, I challenge you to actually write out a way of constructing that, because every single time you do it, if you actually try doing that, you start with the integers and you add on some fractions, you add on all the halves, all the points in between each of the integers, and you then add on all the thirds, and then you add on root 2, and then you add on root 3. You'll never ever finish. It will go on, and you'll always find that you miss some. So how do we actually characterize this this seemingly uncharacterizable set? Well, the genius of Dedekind was to realize that if you take any two points, oh, this stupid camera, any 2 points, I'll try and not move too much, any 2 points on the it's better if I just gesture with the pen, that doesn't seem to upset it. Okay, so any 2 points on the one-dimensional continuum here, and there will always be a rational number in between those 2 points, is what the basis of the Dedekind cuts is based on. Is that if you take any 2 points on this one-dimensional continuum, you will always be able to find a rational number in between there, and the rational numbers are characterizable. The rational numbers, remember, is the set which contains all equivalence classes of ordered pairs of integers. So where you define an ordered pair, 2 ordered pairs to be equivalent if so you make ordered pairs. You make A and B, where A and B are both elements of the integers. So you let A and B equal any number as long as it's an integer, and then you collect up loads of these ordered pairs such that if you have another one here, A prime, we'll call it A bar actually, B bar, then these two are equivalent. They're collected into a single set if A B bar is equal to B A bar, which you'll recognize from normal fractions, because AB is effectively just like AB. And this one's effectively like A bar, B bar. And when will they be equal? They'll be equal when that is satisfied. So you group up these ordered pairs into these equivalence classes, and then these equivalence classes represent the rational numbers. So the rational numbers are constructible. They're also countable. You can find this out. I mean, there are loads of videos just showing how the rational numbers are countable and then the real numbers are uncountable. So that's not really what I want to talk about. I want to talk about how I want to show you the proof that basically there will exist a rational number in between any 2 points on this continuum. I'm going to show you that proof, the proof that I like anyway, best. There are probably loads of them, but what we then need to realise, if this is really true, that between any 2 points on the continuum you can find a rational number in between there, then we can use this fact to distinguish between these 2 points and to characterise these points. So we can say that all the rational numbers to the left of this point here characterise that point on the continuum, because if you take any other point on the continuum, we can prove that there's a rational number in between them. Therefore, all the rational numbers to the left of this point cannot possibly be the same as all the rational numbers to the left of this point, because there's one in between them which won't be to the left of this point. So that's the concept of a cut. All the Dedekind cut, all the rational numbers to the left of a point on the continuum, and we can prove thus, and I'm going to show you how to prove, that if you take any other point on this continuum, that it will be characterised by a different Dedekind cut, and it must be characterised by a different Dedekind cut, because I can find you a rational in between them, which thus can't be in the cut of this other one. Okay, so I'm going to halt the video here, and we'll continue this in the next video.